taking another approach to Riemann hypothesis. I think I was kind of obsessed with, achieving the lowest modulus, but that's actually just part of it. And so I created this dashboard, and basically I'm looking at the cosine and sine and the modulus, created this box, and see how, both behaves as n increases. And so it's all in like a dot, kind of treating it like a molecule. The lower it goes, that's the closest to zero, so you wanted it to be reaching lower and lower. Same with the modulus. And there's also a shift. The dot changes colors to red when it shifts to the negative. Right, so we also see that, but then both are in like the same absolute value, because really what we want is just whatever sign it is, it has to be low value, so closer to zero. And so what I found is that there's another side to the zeta zeros. So I'm like, oh, it didn't reach, no matter what I do, it's not reaching 0.0000. That's kind of my expectation. But what I found instead is a continuous, progressive, every n decline in modulus. So it depends on like what's the limit. If I set it at 0.10, then you see it starting at that, and once it hit a certain stability, it's actually every n that it decreases. So how I set what's the starting was actually the max value of the modulus for that range, that 40 that I retrieve in dashboard 1, get the maximum and then round it up. And you might think, why not just a specific number? It's because it really does increase or decrease so much, like starting from this, and it's so successive that I just want to record at the point in which it's almost at the lowest. But if you go on and wanted like a higher number, like just record at 0.10, that's low enough, then you can do that too. And it actually also records using text files. So like if you want to review it again, you don't have to do the simulation, the whole thing. It's also recorded via text files, in folders. So I've tried other combinations or even shortened the decimals. Even at 8 decimals, it still behaves that way. But if you use like 4 decimals, that's when you don't really see the harmonic divergence or something, or convergence. You don't really see that it declines every nth. So you actually need to have greater than 4. Better if it's 8, if you have the whole 8 decimals. So it does matter, to be precise, to have that entire that exact decimals. So I tried maybe just 2 decimals and then increase it a bit, and then you see that it's no longer have those features. You change the sigma, same t number, 31 decimals, change the sigma to the left, right, by just 0.005, and you don't see that anymore. Does it happen always at different, and maybe I change it to just the number and then 0.001, basically a non-zeta number. And all other combinations, they might achieve a lower modulus. Like I said, it's the modulus itself is just part of the picture, just one part of it, but it does not achieve those effects. It's not continually decreasing. And also, what I find is that my estimate for n, which is the log of 1.57, or basically 43% of t, and then round down, is actually better to do a round down, is quite a valid, and in most times that's actually where it stops. that's actually where the low modulus is. And it might just be -1, -2, or +1, but somehow that approach is actually quite valid for many of the teas um, that I have tested. So so I'm glad to do this again. I'm glad to like think about how else can I um, understand the Riemann hypothesis, from what angle, what perspective, so I'm glad to be like, how does the cosine and sine actually interact? Like, what do I see it? Like, how close are these together? Like, how the zeta outputs? Like, and it seems that once it reaches a certain stability, it actually is there. And even after that low modulus, where it stopped achieving lower and lower, it actually, the cosine and the sine are still within the same range, the same box range, as you can see in that table, that depiction. That it doesn't like suddenly goes, it doesn't suddenly be like greater than 1. So yeah, and then the non-zeta didn't even, was not below 1, or not below, you know couldn't it didn't even get closer to 0 at all. So if it's a non-zeta, then you don't see it even decreasing. So those, what that tells me is that those numbers, the database is definitely valid. They're not really just a made up number. It is really, you can really see that it truly is a number um, that is special, that is, that is, and it's even more special because you see that it's not always like that. That you see other numbers, you plug in other numbers, other sigma, and it does not create those effects, those ever increasing, and as it producing lower and lower modulus. So